Download this code from codegive.com, link in the description below. 3D lidar annotation, challenges, solutions, and a code example. 3D lidar annotation is a crucial step in developing autonomous driving systems, robotics, and various perception-based applications. It involves labeling 3D point clouds captured by lidar sensors to identify and categorize objects in the environment. However, annotating 3D lidar data presents unique challenges. This tutorial will delve into these challenges, explore various solutions, and provide a code example to get you started. Challenges in 3D lidar annotation *. 1. Data sparsity and irregularity *. Challenge * lidar point clouds are inherently sparse and irregular, meaning the density of points varies across the scene and is often much lower than in 2D images. This makes it difficult to accurately delineate object boundaries. Solutions *. Point cloud denoising and filtering * employ filters like statistical outlier removal, radius outlier removal, or voxel grid downsampling to reduce noise and improve data quality. Point cloud completion * use techniques like interpolation, surface reconstruction, or deep learning based methods to fill in missing points and create a more complete representation. However, be cautious about introducing biases with synthetic data. Sensor fusion * integrate data from multiple sensors, example lidar and camera, to complement each other. Projecting 2D bounding boxes from camera images onto the 3D point cloud can provide initial guidance. Adaptive annotation tools * utilize annotation tools that adjust dynamically to point density, allowing annotators to work effectively even in sparse regions. 2. Lack of texture and color information *. Challenge * unlike cameras, lidar sensors primarily capture geometric information, distance. The absence of texture and color makes it harder to distinguish objects with similar shapes and sizes. This is particularly problematic for differentiating between similar vehicles or classifying vegetation. Solutions *. Intensity information * leverage the intensity values returned by the lidar sensor, which represents the reflectivity of the object's surface. Different materials reflect lidar beams differently, providing a hint of appearance. However, intensity is heavily influenced by sensor calibration and weather conditions. Sensor fusion, again, integrate camera images. Project the color information from the camera onto the corresponding 3D points. Contextual reasoning * provide annotators with access to surrounding objects and scenes to assist in contextual classification. For example, a mailbox is likely next to a house or road. Semantic segmentation * use pre-trained models, or fine-tune your own, for semantic segmentation of the point cloud. This can provide a foundation for object detection and classification, reducing the burden on manual annotators. Correcting the output of these models can be faster than annotating from scratch. 3. Occlusion *. Challenge * objects in the scene often occlude each other, making it difficult to see the entire geometry and accurately label partially visible objects. Solutions *. Multi-frame aggregation * combine data from multiple lidar scans taken from different viewpoints over time. This helps to reveal hidden parts of objects as the sensor moves around. SLAM, simultaneous localization and mapping, algorithms are crucial for accurately aligning point clouds from different frames. Point cloud prediction / completion * use machine learning models to predict the shape of occluded objects based on the visible parts. This is particularly useful for common object types like cars or pedestrians. Careful annotation guidelines * establish clear annotation guidelines for dealing with occlusions. For example, define a threshold for the percentage of an object that must be visible to be labeled. Perspective manipulation ** allow annotators to rotate and view the scene from different angles, making it easier to discern partially occluded objects. 4. Annotation tooling and efficiency **. Challenge * creating efficient and accurate 3D lidar annotations requires specialized software tools that can handle large point cloud datasets and provide intuitive interfaces for annotators. Manual annotation is time-consuming and labor-intensive. Solutions *. High-quality annotation tools * invest in, or develop, annotation tools with features like interactive visualization * support for zooming, panning, rotating, and slicing the point cloud. Bounding box creation * efficient tools for drawing and adjusting 3D bounding boxes, cuboids. Polygon annotation * support for free-form polygon annotation for more complex object shapes. Semantic segmentation tools * ability to paint individual points with semantic labels. Keyboard shortcuts * extensive keyboard shortcuts to speed up the annotation process. Data management * tools for managing, filtering, and versioning annotation data sets. Quality control * built-in quality control mechanisms to identify and correct errors. Active learning * use active learning techniques to prioritize data points that are most informative for the model. This can significantly reduce the amount of data that needs to be manually labeled. Automated annotation – pre-labeling employ pre-trained models to generate initial annotations automatically. Annotators can then review and correct the pre-labels, significantly speeding up the process. Human-in-the-loop learning * train models interactively, incorporating feedback from annotators to improve performance. 5. Data volume and storage * Challenge * 3D lidar datasets are typically very large, requiring significant storage space and processing power. Solutions * Data compression * utilize point cloud compression techniques, example octree-based compression, to reduce the storage footprint. Cloud-based annotation * leverage cloud computing platforms to store, process, and annotate large datasets remotely. Data partitioning * divide the dataset into smaller chunks for parallel processing and annotation. Streaming * implement efficient streaming techniques to load and display point clouds without loading the entire dataset into memory. 6. Annotation consistency and quality * Challenge * maintaining consistent annotation quality across large datasets and multiple annotators can be difficult. Variations in annotation styles and interpretations can lead to inconsistencies that degrade model performance. Solutions * Detailed annotation guidelines * create clear and comprehensive annotation guidelines that define specific rules for object classes, bounding box sizes, occlusion handling, and other scenarios. Annotator training * provide thorough training to annotators to ensure they understand the annotation guidelines and can apply them consistently. Quality control checks * implement a quality control process that involves reviewing and correcting annotations by a team of experienced annotators. Calculate inter-annotator agreement, example using intersection over union, IOU, for bounding boxes, to identify areas of disagreement and refine the guidelines. Feedback loops * establish feedback loops between annotators and model developers to identify and address annotation errors and improve the overall quality of the data. Annotation tool features * use tools with features like annotation history * track changes made to annotations to identify potential errors or inconsistencies. Annotation templates * provide templates for common object types to ensure consistency. Automated error detection * implement algorithms to automatically detect potential annotation errors, example invalid bounding box dimensions, overlapping objects. 2. Code example, basic 3D bounding box visualization with Open3D. This example uses Open3D to visualize a point cloud and interactively create 3D bounding boxes. It's a simplified example and doesn't include the full complexity of a production-ready annotation tool, but it demonstrates the fundamental concepts. Explanation asterisk. 1. Dependencies asterisk requires Open3D and NumPy. Install with pip install Open3D NumPy. 2. Bounding box creator class asterisk. __init___ asterisk. Loads the point cloud using o3d.io.read_point_cloud. Make sure you have a .pcd file in the same directory, or provide the full path to one. The default bunny.pcd can be downloaded from the Open3D website, or you can replace with your own lidar data. Initializes the Open3D visualizer. Stores the point cloud data. Initializes lists for bounding boxes. Registers mouse and key callbacks for interaction. Mouse_callback asterisk. Handles mouse clicks. On the first click, it finds the nearest point to the mouse click position and sets it as the start_point. On the second click, it sets the end_point and calls create_bbox. Create_bbox asterisk. Calculates the minimum and maximum coordinates of the bounding box based on the start_point and end_point. Defines the 8 corners and 12 lines of the bounding box. Creates an o3d.geometry.line set object to represent the bounding box. Adds the bounding box to the visualizer. Finish_bbox asterisk, a placeholder function that could be used to save the current bounding box or transition to a new annotation task. Delete_last_bbox asterisk, removes the most recently created bounding box. Run asterisk, starts the Open3D visualizer. 3. Main execution block asterisk. Loads a point cloud. Creates a bounding box creator instance. Runs the annotation process. Prints the number of created bounding boxes. How to use asterisk. 1. Install dependencies asterisk pip install Open3D NumPy. 2. Download a .pcd point cloud asterisk. You can find sample point clouds online or use your own. Place it in the same directory as the Python script. 3. Run the script asterisk python your_script_name.py. 4. Annotation asterisk. Left click to select the first corner of the bounding box. The script finds the nearest point to your click in the lidar point cloud and sets that as a bounding box corner. Left click again to select the opposite corner of the bounding box. Press spacebar to complete the current bounding box. This function is currently a placeholder, it does nothing. Press D to delete the last bounding box created. Use the mouse to rotate, pan, and zoom the view. Close the window to exit the annotation process. Further enhancements asterisk. Saving annotations asterisk. Implement code to save the bounding box coordinates and object class labels to a file, example JSON, CSV. Object class selection asterisk. Add a GUI element, example a drop-down menu, to allow annotators to select the object class for each bounding box. Pre-labeling with a model asterisk. Integrate a pre-trained object detection model to automatically generate initial bounding boxes, which annotators can then refine. More sophisticated mouse interaction asterisk. Implement more intuitive mouse interaction for creating and adjusting bounding boxes, such as dragging corners or faces. Multi-frame annotation asterisk. Extend the tool to support annotating multiple frames of lidar data and track objects over time. Active learning integration asterisk. Prioritize frames for annotation based on model uncertainty. 3. Key considerations for building a production-ready 3D lidar annotation tool asterisk asterisk. Scalability * design the tool to handle large datasets and multiple annotators. Performance * optimize the tool for fast loading and rendering of point clouds. Usability * provide an intuitive and user-friendly interface for annotators. Quality control * implement robust quality control mechanisms to ensure annotation accuracy and consistency. Customization * make the tool customizable to meet the specific needs of different annotation projects. Integration * ensure the tool can be easily integrated with existing data pipelines and machine learning frameworks. 4. Conclusion ** 3D lidar annotation is a complex but essential task for developing perception systems. By understanding the challenges and implementing appropriate solutions, you can create high-quality annotation datasets that enable accurate and reliable object detection, tracking, and scene understanding. This tutorial provides a solid foundation for getting started with 3D lidar annotation and serves as a springboard for building more sophisticated annotation tools and workflows. Remember to prioritize data quality, efficient tooling, and well-defined annotation guidelines for optimal results.